Hi, today I'm going to show you how to solve this problem with a min heap. Fair warning, if you check LeetCode and look at some other solutions, you can see a binary search solution, which has a better time and space complexity, as well as a quick sort or quick select solution, which is better. These solutions are a little bit more complicated, so I'm going to stick to this min heap solution just because it's shorter and I think it's easier. So, let me explain the solution. Let's talk about the problem first. We have two inputs. We have points, which is an array of arrays, which each sub-array is the x, y coordinates for the point. Okay, and then we have k, which is just a number. It tells you how many points you need to return for how many, uh, like the k closest points. If k was 2, we need to return both of these. If k is 1, we need to return only the closest one. All right, and we need to return an of array of points. So the xy coordinates, all right? All right, so the most important thing to this problem for calculating the distance is we need to use this equation right here, found right here. But we can simplify the equation, and let me tell you why. Because the second x and second y is always 0, so any number minus 0 is just going to be the number. So we don't need to do the subtraction part, and we don't need to do the square root because we only care about which one is larger. If you do the square root of 9, it's going to be larger than the square root of 4. So that means we can omit this step and just simplify this entire equation to x squared, this syntax means squared, plus y squared. In this case, it's the index 0 and index 1 for x and y. All right, so it's simplified very much. All right, so the first step, let's step through our problem here. The first step is to create the min heap, and we're going to calculate the total distance, just like I said before, which is x squared plus y squared. So thanks to this data structures package, we can just create a min heap using new min priority queue, which is the same thing as a min heap. Then we're going to loop through each one of the arrays inside of the larger array. So point is an XY array, all right? And that's why we can get the index 0 and 1. And later we're going to add that point array to our um, min heap, okay? Which is an important step. But first, let's talk about this enqueue function because the enqueue function is a little tricky. It actually is going to create an object. The first point is going to become the element, and the second argument, the total, is going to become the priority. So later we're going to destructure that out. So just keep in mind we can use object destructuring just to get this point, and then we'll push it into our closest points array and just return that. All right, so let's walk through it. We do negative 2 squared plus 2 squared, because that's our first right here. Those are inputs for points, our first example, and that equals 8. So our total is 8, and our point is negative 2, 2. So we push that in, and basically this is what it will look like. Priority 8, element negative 2, 2. Okay? And we do the same thing for the next point, 1, 3. So the total is 10, and we're going to push that in. Priority is 10, element 1, 3. Now we need to go to the second step. All right, let's get that out of here. And we're going to dequeue the smallest point, or the root. So whatever is in the front, using this front function. But remember object destructuring. And let's talk about the while loop. So k is 1. The first time it goes through this, k is going to be 1. So it's greater than 0. The second time it goes through it, we're going to decrement k by 1. And it's going to be 0. So we'll stop. All right. So we dequeue that front, just the element. Okay. Front has priority and element properties. We just take the element, which is our array of the points, x and y, which is awesome because we can directly push that into our closest points array, and then all we have to do is return our closest points. And essentially what this would happen is we'd pop off this point from our min heap. Our min heap would become this, and we return closest points. Let's talk about the time complexity. So the first step is going to be n, because creating the heap for the size of points is going to be an n operation. Each insertion is going to be log of n, but we're going to simplify it to n. And dequeue, this gets a little tricky because we have to dequeue for the size of k, but each dequeue operation is log of n because our min heap was created for the size of n. So that's our total time complexity. Space complexity is just for the size of the min heap that we create, which is the size of points. All right, that's it.